This video will be a walkthrough of proving the Pythagorean theorem using similar triangles. What we're going to do in this video is essentially two major sections that allow us to get from a right triangle all the way to the Pythagorean theorem using similar triangles. So the first half of the proof is going to require us to construct an altitude in a right triangle. And then what we're going to end up with are three similar triangles. We're going to have to prove that they're similar. And then we're going to obtain two proportions that we are then going to manipulate using algebra to get down to the Pythagorean theorem. So the first part is the part with the triangles, constructing the three triangles, establishing the corresponding sides, proving that they're similar, all to get our step number 7 here, which has the two proportions there. So the first half of the proof is all the similarity portion, and that is just to get these two equations right here. From there, the rest of the proof is algebra. All right, so you can see it's just a bunch of algebra for the second half of the proof. All right, so there's two main parts, the similarity part and then the algebra part. So let's go ahead and start off with the similarity part. The reason I have these triangles over here is because this is going to make it easier for us to match up the corresponding parts of our three triangles. So we're given a right triangle and we are asked to prove the Pythagorean theorem. So here we go. The first thing that we're going to do is look at our proof. All right. Now, because we have all the statements, that serves as a type of guide that can help us work through the Pythagorean theorem. You guys aren't really proving things from scratch. You're not even really filling out two-column proofs from start to finish. You're really just recognizing the steps and making sure you understand the different components of the proof. And that's what you will essentially be tested on your unit tests and your FSA at the end of the year. So the first real step tells us to draw the altitude from the hypotenuse to the right angle. So let's go up here to our triangle, and we actually learned how to do this back at the beginning of the year, constructing a perpendicular to a line through a point. The point that we're going to be going through is y. Let me get a more gooder marker here. The point that we're going to be going through is y, and we're going to construct an altitude there. Now, we could get very formal and precise and use a compass and a straight edge. We're not going to do that here. We're just going to draw our altitude and label it as intersecting at a 90-degree angle. So this would be an altitude. It's going through the vertex y to the hypotenuse of the right triangle XYZ, and we can see there that it's intersecting at a 90-degree angle. We're going to label this W, and that's what they want us to do for step 2. So all we really did there was to construct. So we're just going to say by construction, we made an altitude perpendicular to the hypotenuse. So there we go. That's step 2 right there. Now we're stating that XWY and YWZ are right triangles. So let's look at our picture. Let's see what we have to work with here. Because we constructed an altitude, we know that both of these angles are, in fact, right angles. And so the first triangle we're looking at is XWY. XWY is this small triangle right here. And we can see that that is a right triangle because it contains a 90-degree angle. The other triangle is YWZ. So YWZ is the other smaller triangle. YWZ. So that is the other smaller triangle that I'm just going to color green here to make it stand out a little bit better. And that is also a right triangle because, of course, there's that 90-degree angle that is constructed by the altitude. So we're going to say that these are right triangles by the definition of an altitude because that required us to construct a 90-degree angle, which in turn made those two triangles right triangles, right? So we're moving right along here. Now this is the tricky part where we have to establish all of these similarity or prove all these similarity statements. So now we're going to switch gears and we're going to go over here to our diagram. So I've got my blank triangle here. I'm basically just going to copy the picture from my proof worksheet right up here. So the big triangle is triangle XYZ, all right? So that's the big triangle there. So this is X, this is Y, and this is Z. Just copying this picture over here. onto my larger diagram that I'm going to highlight and such. All right, the point of intersection is W, and we know that this is the right angle, and this is the right angle, and this is W right there. We have the sides labeled. The sides are labeled A, B, and C. And that's it so far. All right, now for simplicity later on in our proof, we're going to go ahead and add a couple of extra names here to some of the sides of the triangle. So this side of the triangle has a name, this side of the triangle has a name, this whole side of the triangle has a name, but we want to go ahead and name these three smaller parts just so we can easily refer to them as we need to. So I'm going to call this shorter part of the hypotenuse P. That's just from here to here. All right, so this part is P. Can make it look fancy. Let me move this over. Make this look fancy right here. And then the other part of the hypotenuse, let's go ahead and call that Q. All right, so let's go ahead and call this other part of the hypotenuse Q. And again, this is just to make it easier to refer to later on. And then the entire hypotenuse is C. And let me go ahead and put W back there. All right, so that's W. So our point of intersection with the hypotenuse and the altitude is W. We have P, we have Q, and together they give us the entire hypotenuse, which is C. All right, so now we've got these smaller triangles down here. All right, these triangles down below. And what we're going to do is we're going to label them based on our larger triangle up above so that we can easily prove that they are similar. So let's go ahead and highlight some of these sides here to help us out. So I'm going to highlight side A yellow. This is yellow right here. Let's highlight side B blue. And let's highlight the hypotenuse. Let's break it up into a couple different colors here, because since we've broken up the hypotenuse into a couple pieces. So let's highlight this side pink, and we'll highlight the other side green. Now this side here, we can go ahead and label that H. This part of the triangle, the altitude that we constructed, isn't really going to serve much purpose from here on out. So now we're just going to take this triangle and break it apart into these three other triangles and label it accordingly. All right, so first of all, let's talk about orientation. If I were to take the triangle as is, so let's say that this is my triangle right now, XYZ, all right? So if this is my original triangle, if I rotate this triangle and then reflect it like that, I get the triangle right here. All right? So again, if I take this triangle, rotate it, and then reflect it or flip it over, that's how I get this triangle right down here. So I'm going to go ahead and label it. So the right angle is still Y. X will be here, and Z will be up here, because we've taken this triangle, we've rotated it, and we've flipped it. And the reason we're doing that is because we're matching the orientation of that triangle to our other triangles here. Now if I do that, the hypotenuse is still going to be C, all right? The shorter side is still going to be A, and this side is still going to be B. So let's go ahead and color code that accordingly. So B was blue, and A was yellow. And the hypotenuse was pink and green, right? So we'll just leave that as is. So there's our colors right there matching our larger triangle. This triangle, the medium-sized triangle, comes from right here. So if I were to take this triangle, the yellow one, and just rotate it and slide it down, that's where the medium triangle is coming from. All right, so let's look at that. This is Y, this is W, and this part is Z. So when I bring it down here, that still holds true. So the right angle is W. This smaller angle here is Y. It's not the same Y as this one here, so it's a little bit different because it's just a piece of that right angle. And then up here, this is Z. And let's go ahead and highlight and label the sides. So this portion here is the hypotenuse of that triangle, right? So this length here is B. This little short side here is H. And then you've got the portion of the, or you've got the other leg there, the portion of the hypotenuse that we've gone ahead and labeled Q, and we colored that green to distinguish it from the other ones. So we'll label this Q, and we're going to go ahead and highlight that. So Q is green. H we're not going to bother highlighting, and B was blue. Right? So that helps things stand out. And again, this is all going back to our original diagram. Last triangle, and then we can actually start doing some stuff. Last triangle is that little triangle right there. So the little part of the triangle that's right here, so it's basically in this orientation right here. So if I take that little triangle and rotate it and slide it, that's where the small triangle comes from, okay? So again, it's in this orientation, I'm rotating it and sliding it, and that's where it's coming from. So the right angle of the small triangle is still W. This little piece right here is this piece up here, which is X. And then this part of the triangle is actually the other little part of Y right there. So in between X and Y, we have A. So this is A. In between X and W, according to my picture here, notice that that is P. So we're going to label this P. Oh, I meant to do these in different colors, sorry. This was A and P, right here, A and P. And then this portion here, YW, is the same as this, which is the same as this, which is the height, which is not really that important for this proof, but just so we have it labeled. So side A, we originally highlighted yellow, so let's highlight that yellow. Side P, we originally highlighted pink, so let's highlight that pink. Okay, so there we go. So we've got all of the corresponding parts of our triangle labeled. So now really it's just a matter of dealing with these three triangles to establish our proportion. So let's go ahead and zoom in here. Zoom in on our three triangles. Okay, so from that initial triangle, we now have these three triangles, and all of this is just to establish first similarity and then to establish that proportion for step number 7. That's what we're trying to do for this first half of the proof. All right, so let's see if we can prove that these triangles are similar. So for simplicity, I'm going to label these as big, medium, and small. All right, so now let's mark what we know. So we have three right angles, so automatically we know that those are all congruent. We can see that angle Z is going to be congruent to angle Z for the big one and the medium one. And then angle X is going to be congruent to this angle X over here. All right, now it's hard to see Y and Y right here. All right, because see how we divided up? See how we've divided up that right angle right there? I don't necessarily know that these are congruent just by the way it looks, so I'm just going to leave those unmarked for now. All right, but we definitely know that Z, all right, is congruent for the big triangle and the medium triangle, and we definitely know that X is congruent for the big triangle and the small triangle there. So let's just leave those marked as they are. Okay, All right, so let's go to our proof. The first similarity statement says that XW is similar to XYZ. So XW is similar to XYZ. So XWY, excuse me. So XWY is the small triangle and XYZ is the big triangle. So right now we want to prove that these two triangles are similar. Well, right off the bat, they're both right triangles and they both have this angle X in common. So that is angle-angle similarity there. So I can go ahead and fill that in on my proof over here. Angle-angle similarity. The next similarity statement, they want me to prove that YWZ, again, YWZ, that's the medium triangle, is similar to XYZ, which again is the big triangle. So if we want to prove that these two are similar, again, we can see that they're both 90-degree. They both have 90-degree angles. Those are all right angles are congruent, and they both have this angle Z in common. So again, there is our angle-angle similarity. Okay? So those are also similar. So far in our proof, we've established that the small triangle is similar to the big triangle, and we've established that the medium triangle is similar to the big triangle. Well, if the small is similar to the big and the medium is similar to the big, what other relationship is also there? The small triangle has to be similar to the medium triangle, all right? So if this one is similar to this one, and this one is similar to this one, so small to big, medium to big, then it also follows that the small triangle has to be similar to the medium triangle. Both of these triangles are similar to the big triangle, so that must mean that they're also similar to each other. So that is the transitive property that we're using. So right here for step 6 is going to be the transitive property. Again, if both of the triangles are similar to the big triangle, then they also have to be similar to each other. All right, that's logically how it would go. So now the first half of the proof is complete. So we no longer need these three triangles. We're still going to use it to just double check our ratios are correct. But that's the point of having these three triangles, is to establish similarity so that we can get the proportions. All right, so let's go ahead and just look at the two proportions that we're working with in the proof, and then we'll just double check them with our three triangles to make sure that it makes sense. So we want that A is to P as C is to A. That's the first one. And then the second one says Q is to B as B is to C. Okay, so let's go ahead and compare these proportions to our three triangles that we have. Oops, let me zoom out. Okay, so there's our three triangles, and here are our proportions. All right, so A is to P as C is to A. Let's go ahead and see if that's true. So P only appears in the small triangle. So we're looking at the small triangle, and we're looking the only other place A appears is the big triangle. So we're comparing the big and the small right now. So A is to P, those are corresponding sides. A is to P as C is to A. All right, so A is to P as C is to A. It also works this way. A is to P as C is to A. All right, so notice that when you have corresponding parts, it doesn't matter if we can go big to big, big to small, small to big, small to big, small to small, big to big, as long as you go in the same order and you're consistent. So either way, we can say that that is true. All right. The next one, we can say that Q is to B right here for the medium triangle, as B is to C. We can also, it works the other way as well. We can say Q is to B as B is to C. Either way we look at that, you're matching up corresponding parts and you're going consistently in the same order. Okay, so both of these are true based on our three similar triangles. So that's it for our triangles. They served us well. Now comes the fun part of the proof. Now comes the algebra. All right. So basically, we're just going to be working our way through the second half of the proof until we get the Pythagorean theorem. All right, so there's really only one thing that we think to do with proportions, and that's to use the cross product property. So I'm going to cross multiply both of these, and when I do that, I'm going to get two equations. A times A is going to give me A squared, and P times C is going to give me CP. I'm just putting them in alphabetical order. Likewise over here, B times B is going to give me B squared, and that's going to be equal to CQ. So there's my two equations. All right, so I want to start getting the Pythagorean theorem. So how can I get the Pythagorean theorem from these? Well, I know that I need A squared plus B squared somehow. So if I add B squared to both sides of this equation, I'm going to start getting somewhere. So let's go ahead and do that. A squared plus B squared equals CP plus B squared. This looks good. This doesn't look like C squared yet, but again, we're getting somewhere. So if I look over here, B squared, according to my second equation, B squared equals CQ. So I can use substitution to replace B squared with CQ anywhere I want to. So the left side of the equation is going to stay the same for now. I'm going to go ahead and substitute in CQ. And now I have a C in each term. So if we keep moving down the line here, both of these have a C in common. And as soon as I see that, I'm going to think of factoring. So I'm going to factor out C, just like when I factor out the greatest common factor in algebra. So now I have C times the quantity P plus Q. All right, well, I know that I'm trying to get this side to be equal to C squared. I know that. And if we look back at our original diagram here, our beautiful colorful triangle, I can observe that P and Q together are the same length as C. So C is equal to P plus Q. So again, I'm going to use substitution. So this is now equal to C times C. This is substitution, which when we simplify is C squared. And there is my Pythagorean theorem. All right, and these are the steps that we need to take in our proof as well. So there's a overall shot of all the algebra that we need to do in this proof. So there's a couple different things going on here. We're using the cross product property. We're using substitution a couple times. We're factoring. All right, so those are all things that algebraic techniques that we're using in this proof. Let's go back over here to our actual proof and fill in all of the steps. So now I only need to concern myself with the bottom part of the proof. So first of all, our ratios came from the fact that those are properties of similar triangles. That's a tilde, not a very good one. When I cross multiplied, we can say that we use the cross product. Adding B squared to both sides is nothing more than the addition property of equality. When I substituted CQ for B squared, that's the substitution property. No surprise there. Then I factored out C, which is the distributive property in reverse, but it's still the distributive property. All right, reverse distribution is not a real thing. We call that factoring. But that's still the distributive property. When I replace P plus Q with C, that's substitution again. Well, more specifically, it is substitution, but more specifically, it's the line segment addition postulate that says that. All right, line segment addition says that P plus Q is equal to C, so that's more specific with that. And then the last step is, of course, just simplifying. We're simplifying to get A squared plus B squared equals C squared. All right, so there is our Pythagorean proof using similar triangles. All right, I hope you guys find this video useful and happy studying.